Okay, so I think I'll start. What we had last time, I talked about the distributed ray tracing paper in terms of the motion in time and the position on the lens and the position on the pixel. But that paper also talked about glossy reflection and sampling glossy reflection. And I want to review something I said last time about glossy reflection and then say how you might sample it. So what I said is if we consider the Phong BRDF, here's psi and here's theta. That was Ks, some specular coefficient, times the difference between theta and the perfect reflection of the incoming ray. Psi is the incoming ray, and this is the surface normal. And the reason this is in the denominator is because the Phong formulation had the cosine term, this dot product, multiplied by the BRDF. And his formula was just like this, with some exponent. And what I said last time was if you look at this normal, and here is, say, I don't remember whether I drew this one higher or lower then. Let me just say here is the reflected direction. I don't even remember whether it was to the left or the right. And here is the incoming direction, psi. And here is the mirror image of the incoming direction, which is this direction r, that you're supposed to measure this angle alpha with. And what I said is if you take these two vectors and rotate them 180 degrees around this normal, I didn't exactly say it that way, but it occurred to me here's a better way to say it, then r will be rotated into this incoming direction because it's the mirror reflection of it, and theta will be rotated into another direction, which I called m. And this angle here will be the same as that angle there because it's just a rigid rotation of both of those vectors. And so if you write this instead as Ks of m dot incoming direction to the nth power and nx, this is easier to handle. Because what you're doing is you're sampling the incoming direction, and then you're computing an FR based on it. And so that's what I want to do. That's what they meant by sampling the glossy reflections. You're sampling around this perfect mirror of the viewing direction. So you want to generate a bunch of random rays here so that their probability distribution is proportional to this factor FR x psi theta times the cosine nx dot psi. Right? And that will just be this thing. Because we're going to have these two factors are part of the integral of L. And so if we sample with a probability proportional to this, then that probability will be in the numerator of what we're trying to integrate, and it'll also be in the denominator because, you know, when we have sample according to probability, we always have to divide by that probability, and those factors will cancel, and we just be sampling incoming illumination. So what we need to do is design a probability function which is proportional to the cosine factor and the BRDF factor. So proportional to just this Ks is a constant, right? What we're really interested in is this thing. cosine to the nth alpha, where alpha is the angle between the perfect reflection vector m and the particular sample direction psi we're picking according to this probability distribution. So say the probability of a given direction psi is some constant times cosine to the n of alpha. Okay, and I'm going to assume that this probability is very low for large angles. So I'm going to make it add up to 1 over the hemisphere that's perpendicular to n. I mean, that for m as the North Pole. So really, I'm actually distributing it around a hemisphere like this, around m. That wasn't very beautiful perspective, because and m isn't even the center. Maybe I should correct it a little bit. This is the part of the paper where they said choose the samples near the perfect mirror direction. So the perfect mirror direction is supposed to then be the North Pole of this hemisphere. And you can see if the base of this hemisphere, this equator line, is tilted with respect to this horizontal line, that won't be exactly right, because there could be some directions here which are actually below this plane. But those will have very small probability if the exponent n is high enough. And if you get one, I guess you just throw away and try again or something. So what I really want to do is I want to normalize this over this hemisphere where this cosine is non-negative. So that's very similar to what we did before. Basically, if I draw a bigger picture of this sphere here, we can now think of alpha being the angle between the sample. Here is m, and here is the sample. And this time I drew it a little bit above m. And we can also pick an x-axis here and project it down and find a phi, which says how far it's oriented in the other direction around that sphere. This will be the alpha is going to be related to the latitude. I guess it's 90 degrees minus the latitude, or latitude minus 90, some deal like that, because latitude starts at 90 at the north hemisphere rather than 0. But it's basically measuring that polar angle, and phi is measuring the azimuthal angle. And this distribution is going to be independent of phi, right? So that's a special fact. But the method I'm going to tell you in general, suppose you want to sample a two-dimensional distribution using two random numbers and using that cumulative distribution method. What you can do is pick the marginal distribution with respect to one of them and sample that first. And then once you have that sample, you can sample what's called the conditional distribution for the other variable. Namely, how can you choose the other variable knowing the first variable? In our case, they're independent, but in general, they won't be. And you might get a different marginal distribution for each way you pick the first variable. And so what we're going to do first is sample alpha by the cumulative distribution function of the marginal distribution. And what that marginal distribution means is that for a given alpha, what do I call it? Say marginal of alpha is the integral, in our case we're going from 0 to 2 pi of the probability of alpha and phi d phi. And we'll get the marginal distribution with respect to alpha after you integrate out the dependency on phi. And in our case, that's going to be the integral from 0 to 2 pi of k times cosine to the nth alpha d phi. And this doesn't depend on phi in our case, but in general it might. I'm just trying to illustrate this general method. So what this is going to be is just 2 pi k cosine to the n alpha d alpha. Actually, this is supposed to be, it's not exactly right, is it? Because I forgot my sine alpha term. Right? Because my probability density, instead of being measured per unit area on the sphere, I'm thinking of measuring per phi and psi. And that means I have to take my solid angle where I'm measuring, say, some d omega psi and turn it into sine alpha d phi. So I have an extra sine alpha here that I missed here too. Because I'm thinking now of measuring the probability distribution in terms of these two angles. So I have to get that area factor as part of it. Okay, so now we have the CDF of this function m of alpha, and that is the integral from 0 to alpha of, say, 2 pi k cosine to the n of t sine t. I guess I didn't need the parentheses around either of these. dt. Right? Because this is, I've already integrated out my phi, and now this is just the part in alpha. So this is similar to what I was doing before, right, when I just had cosine and sine last time. What is something whose derivative is this? Well, the derivative of cosine is minus sine. So if I have cosine to some power, right, this is the answer. If you look at cosine to the n plus first power and take its derivative, you'll get, by the chain rule, it's a function of a function, exponent of a cosine. So it's like this. If we write it like that, it's going to be n plus 1 cosine to the n plus, to the nth power, 1 per power less, times the derivative of this, which is minus sine t. Forgot my t's here. Right? By the rule of, it's the power of a cosine. Really, this is cosine t to the n plus 1. That's another way of writing it. So that means that for this integral, CDF of m of alpha, I have to figure out a way of, this thing then is going to be d dt of, well, I'm going to have a minus to cancel this minus, and I'm going to have 1 over n plus 1 to cancel this n plus 1 of cosine to the n plus 1 t. Right? Because, you know, I took this derivative, and then I had to see how I have to fudge this to actually give without the n plus 1 and without this minus sign. So this is the integral, and what that is the integrand, maybe I'll write it here, minus cosine n, plus the thing I took the derivative of here, of t divided by n plus 1, evaluated between 0 and alpha. So at alpha, it's minus cosine to the n plus 1 t over n plus 1. And at the lower limit, it's minus cosine 0. That's minus of minus 1. That's plus 1 over n plus 1. So I guess in terms of a fraction, it's 1 minus cosine n plus 1 of, this is not t anymore, it's alpha over n plus 1. That's the integral without my 2 pi k here. So I forgot the 2 pi k there, so I should have a 2 pi k here too. So, just like last time, what we have to do is choose this k. We said it was the probability function was proportional to this, and k is my proportionality factor. What I need to do with this k is make the probability integrate to 1. Otherwise, it won't be a probability density function. So that means I have to choose k so that when I integrate all the way up to alpha equals 90 degrees, I'll actually get 1. And so when you integrate up to 90 degrees, C, D, F, let's write it of m over pi halves to look fancy. That's 90 degrees. I'm sorry. How can I say this? It's not m of pi halves. It's m, the cumulative distribution function, evaluated at pi halves. Right? You just have to put pi halves in for that. Cosine of 90 degrees is 0. And we have 2 pi k in the numerator and n plus 1 in the denominator. And that answer is supposed to be 1. Right? Because I'm having a probability density function. Its integral has to be exactly 1. So in order to build it, I have to choose the k to make it 1. And that means I have, say, 2 pi k equals n plus 1, and k equals n plus 1 over 2 pi. So what does that say about the Phong distribution? Suppose no energy was lost, right? So you have nothing is absorbed when you hit this glossy reflector. It's just like the little bumps on the glossy reflector are spreading it out, but each of those little bumps is a perfect mirror. Well, then that means 100% of the energy that comes in should be reflected in some direction. And by Helmholtz reciprocity, that means 100% of the energy as integrated over the direction should reflect toward your eye. Basically what it means is if you're going to make a Phong highlight of a point source, the normal Phong formula, the maximum of that cosine is always 1. So as you make those little bumps flatter and flatter, so the surface becomes shinier and shinier, right? Get a smaller and smaller highlight. With that Ks staying the same, your actual reflected energy is going to get smaller and smaller, right? Because the center of that spot is just as bright, but the width is getting smaller and smaller. Well, this compensates for it. It says if you want to reflect 100% of the energy, your K specular has got to be this number. And when n gets bigger, it makes the center of the highlight brighter to compensate for the fact the highlight got smaller. And the 2 pi is in the denominator just like it was for the k diffuse, also to make it integrate to 1. So in terms of sampling, now we know what this k is. So really, what we're going to evaluate, we're going to choose a sample psi from this distribution. And that means first choose alpha. Okay, so what do we want? We want to know that using, say, a random number r with 0 less than or equal to r less than 1, like you get from a random number generator, and make it so that the you find the alpha such that r is the CDF evaluated at that value alpha. And that means what we have to do is, let's see, my distribution function was 2 pi k times this thing. So let's see, it's 1 minus cosine to the n plus 1 of alpha divided by n plus 1 multiplied by 2 pi k let me think. And k was n plus 1 over 2 pi. They cancel. That's what we made them do. So it's just this. That's the random number generator. So cosine to the n plus 1 of alpha. Let's see, if I bring that to the other side, I'm going to get 1 minus r. And if r is randomly distributed uniformly between 0 and 1, so is 1 minus r. So we can call this another random number generator. So let's see, that means that cosine alpha, if I take the n plus root of both sides, is the n plus first root of r1. And that means alpha is cosine inverse of the n plus first root of r1. So last time when we were doing diffuse, we had just the square root. Now we have the n plus first root. Okay, so now, given alpha, choose phi according to the conditional probability distribution. P of alpha phi divided by the probability of distribution of alpha alone. Right? Because if we integrate this numerator with respect to phi, we're going to get a number which isn't always 1. Because it integrates up to this marginal distribution. So if we divide it by the marginal distribution, we'll get the true correct probability distribution for phi once you fix alpha. And things are going to cancel out so that, let's see, probability of alpha was cosine, well, this value of k that we just found, cosine to the nth alpha sine alpha, and see if I do this right, because I need factors of, let's see, this I'm trying to figure out what's happening here. This one, both of these are the same, right? Because it doesn't depend on, this one doesn't depend on the alpha, right? So this is a constant distribution. In some case, in the general case, it won't be, but in this case, it's a constant. And so if it's going to be proportional to some, it's going to be constant, it's got to integrate to 2 pi. That constant has got to be 1 over 2 pi. So we want to choose uniformly in the interval between 0 and 2 pi. And so we'll let phi equals 2 pi times some random number 2 between 0 and 1. And so with those two samples, we can sample the glossy reflection. And that's what they were talking about in that paper. Okay, so now I'd like to continue to what I told you to read in the book. And it was a little confusing, and I'm going to talk about it basically because I told you to read it and I want to explain it. It's just trying to get consistent ways of setting up this Fredholm equation for the radiance that you have to solve when you do any of these algorithms that are trying to do global illumination. And so the original formulation we had was that L starting at x going out into direction theta is LE x going out in direction theta plus a term which was the integral over all solid angles of the bidirectional reflection function x and theta reflecting from psi to theta. It doesn't matter which one you put first because of reciprocity. L, and this is x coming in from direction psi, and then we had the cosine of the angle between psi and nx, d solid angle with respect to psi. And the trouble that this few pages I asked you to read in the book is trying to fix, is that this is coming in whereas this is going out. So it's sort of not a consistent kind of function you're trying to find for. So this mixes incoming or incident, I should say, because the other one is called excident. Incident right here, and excident right here, radiance. So what we're going to do is going to replace one or the other by some formula that only uses what the other one uses. So suppose we want to make everything in terms of excident radiance. What we're going to have to do is, here is x, and here is the excident radius in direction theta, and here's this variable of integration psi. And we want incoming direction from here, but what we'll do is we'll trace this until it hits some other object here at a point y. So y, I think I said before, you can say it is the ray tracing function from starting at x and going in direction psi. And we'll look at the radiation from this point y. I guess if we're going to write it like this, we're assuming that it's a closed environment. Otherwise, it would be the background, the black night sky or something, if there weren't objects above you. Here's a direction minus psi. If you look at the excident radiance from that point y in direction minus psi, that's actually the same as this radiance, but now everything is expressed in terms of excident radiance. So we can say L of x going to theta equals LE x going, this is emitted radiance that you always add if this is a light source, plus an integral over solid angle of now the same FR factor x. I think I'm copying them from my notes so it's in the opposite order, times now the radiance starting from y going in direction, I guess, let's see, if I did it right, it's supposed to be consistent from here, yeah, y going in the direction minus psi. And then this same cosine factor, d omega psi. So the only thing changed is we replaced this by that at a point here where this ray hits, so we could get excident radiance. But we could also do it the other way. We could replace the left-hand side. So let's see, how would we do that? Let me draw a picture here. Here is x. So instead of saying what's going out in direction theta, what we want to know is what's coming into x from direction theta. Right? Because if we want to replace this by incident, we're going to have to say Lx coming in from direction theta is Le incoming. So what does this really mean? What this means is it's the excident radiance from y that's emitted. Right? This term is really Le of y going in direction minus theta. And then to get the reflected radiance from y going in this direction minus theta, we're going to have to add on plus the integral over omega y, right? Because now here is theta. If we trace, I guess we have to trace the ray in the theta direction, and we're going to hit this surface here at point y. And then we have to look over the hemisphere above y and look at incident radiance coming in, excuse me, from direction psi at the point y and going out in the direction minus theta. Because then we have something consistent in terms of incident radius. So let's see, how can I write this? This is Fr at y, and say coming in from psi relating to the direction minus theta. And then the radiance coming into y from the direction psi. And now cosine of the angle between ny and psi. And this is d omega around the direction psi of incoming radiation. So again, we've got, let's see. I wrote this one wrong, didn't I? It's leaving y going into direction minus theta. I got my arrow wrong. And that's the same by conservation of radiance over air or vacuum or something that isn't messing it up between when it leaves and when it gets there. So now everything is consistent. If you write it with this notation, it's all incoming. I was just explaining what the incoming emitted radiance meant when I wrote it this way. I guess, yeah, okay, so I've done both of these, and then you can do the same thing if you do it over the hemispheres. And there's one of the ones in the book that's got a typo, so let me do it over the hemispheres just so I can correct that. I'm sorry, not over the hemispheres, but over the areas. Which is the one that's wrong in the book? Maybe I'll only do that one. Incident radiance integration over surfaces. So now we want L of x coming in from direction theta. And it's going to be similarly LEx coming in from direction theta, which is really what's leaving that point y, plus now we have to write this as an integral, and it's actually an integral over areas of surfaces that come into y. So we have some other surface here. If we extend this thing, it's going to intersect the other surface at some point z. And we want to compute the integral over the areas of all other surfaces as they affect this one. So this is going to be the integral over all surfaces of the scene of, let's see if I can do this right. Fr y, and it's going to reflect in direction minus theta, and it's going to come from this direction from y to z. So this just means the unit vector that goes from y to z. And that's because what we're doing is we're not choosing this direction, we're instead letting z vary over all these surfaces. And so that direction in terms of this z is the direction of the unit vector that would start at y and go to z and then be normalized. And now we have the radiance at z, let's see. How can I say this right? I guess what I have to say is it's incident at y from the direction y to z. And then see if let me look at the book and see what I corrected here. They had a psi there, and I wrote minus theta. And why did I do that? Because it's reflecting here and coming from this direction. And this one, they have an arrow. So I should have written it like that. Coming from that direction, incident on the surface. And now we have the cosine of... Well, that's part of the geometric factor, right? We have the visibility between y and z, and we have this geometric factor which has got the solid angle and the cosine built into it. That should have been yz, yz, and this is dz, the area over this other surface that's illuminating the point y. Right, so this is that solid angle to area conversion using this geometric factor, which had two cosines and 1 over the distance between them squared. And so all I've done is done that thing again, but in the context of now having incident radiance on both sides of the equation, but turning it into an area formula. And you can do the same thing with excident radiance, but I think the book doesn't have a typo in that case. The book had a psi instead of a minus theta here, which I believe was wrong. Okay, so I didn't want to say that much about what the book was doing there. I wanted to continue to actually get ahead of schedule on path tracing. So for path tracing, what we're going to do, like if you do your homework the way I specified it for this time, all it is adding the motion blur and the anti-aliasing and the depth of field. But when you actually pick a ray, you're just going to intersect the surface and figure out the color there, say either by direct illumination and diffuse reflection or recursive ray tracing, if you want to keep your recursive ray tracing as part of that. But that's with the perfect mirror. You're not actually going to cast other rays to sample the illumination. But that's what's required in the third assignment. So if you're going to do path tracing, you also want to get the global illumination from other surfaces at the point you're shading. And we're going to do that by choosing a sample according to some probability distribution, either uniformly on the unit sphere or unit hemisphere, or the way I talked about the last time, weighted by the cosine factor, so you get the stuff that's above the surface more, or if it was going to be glossy, weighted by the Phong, or you might preferentially aim at light sources. However you choose the sample, you're going to choose it by some probability distribution. And so what I want to say is color, a routine color, let me start it higher because it might take a lot of space. Path trace. So you have a position and an angle. And what you want to do is trace a ray from P in direction theta, and if it meets, I guess, two E's, the scene objects, intersects the scene objects at point Q. That Q is what happens when you do the ray from P in direction theta, according to your ray tracing into the scene. Then we'll pick a random direction psi according to a probability distribution P of psi, like the one I derived for the Phong Glossy reflection, if that's how the surface was reflecting. Doesn't matter how you pick it. What you're going to do is return one sample of what you see in that direction. But what you have to do is return first LE at the point Q going into direction minus theta, right? Because this ray leaving, I guess it's similar to the surface I had up here, only I called the point Q instead of Y, in minus theta, toward the, because you're viewing it in the opposite direction, plus an estimate of that integral. So I guess what I should do is compute a factor. Let me erase this a minute and compute the factor that you're going to have to weight that recursive call from. And what it is, it's FR at the point Q for something that enters in direction psi and reflects in direction minus theta. And then we have times the cosine of phi and the normal at Q. No, it's, let's see, it's psi and the normal in Q, the normal cosine factor. And then what we want to divide by is the probability, right? Because when we sample this, we have to divide each sample by the probability we pick the sample. That's the standard way of doing Monte Carlo integration. And now what we're going to return is LE at the point Q going into direction minus theta. That's the emitted stuff plus this factor times a recursive call, path trace, starting out at Q in the direction psi, right? So I'm viewing, say, this eraser. I generate a random ray, and it goes and hits the wall. And then to evaluate what it sees, I get the light emitted by the wall. In this case, it's 0. It's not a light source. Plus the color of the wall, which I'm going to get by recursively choosing another sample in another direction, which may actually hit a light source. And so if you think about this, this is going on forever, calling these, and what it's eventually accumulating is the pieces of light sources that actually hit. It could actually bounce off that fluorescent tube and come and gather some more light that hit the wall, and even though the tube was glowing, it was also reflecting stuff. Okay, and I guess I need an else return some background. The book doesn't think about this. Because the book doesn't deal with the case that it misses everything. So if you do this, you could potentially go on forever. In fact, the way it's written, you will go on forever. And so it's impractical, just like your ray tracing, recursive ray tracing, if you had too many shiny surfaces, you'd get an infinite loop. So we have to break the loop. So the way you did it, broke the loop for homework, was consider a maximum level. And that's one way to do it. You do a level here, and if the level is, bigger than you increment it each time you call, and if the level is bigger than the threshold, you stop. But another way to do it is to keep multiplying these factors together, right? Because the factor really says how much that's actually going to contribute because it's been multiplied by this. So if we have some sort of a weight that says how much that actual color that you return will contribute to the root call that started this whole recursion, then you initially call it with weight 1, and here you call it with factor times weight, and if the weight that you call it with is less than the threshold, return 0. Right? That's the same thing you'd have to do is if this was a count and it got too big, you'd have to return 0. So what you noticed if your count, when the recursive ray tracing was too low, you saw black spots on your spheres. Well, the same way, either by truncating at a given level or by truncating based on how much that new color could possibly contribute after you had all these factors multiplied in this recursive computation of all the factors along the recursive calls that I did by calling it this way. You stop and call it black. In that case, you're also biasing the answer. You're making it a little bit too dark. So next time I'm going to talk about Russian roulette, a way how not to bias it. But today I want to finish just by saying how you would put this call into your distributed ray tracing. So you'd say for each pixel ij, say, we'll start out with a color equals 0, and we'll pick, and then in a loop, say for n samples, pick the subpixel position somewhere in the pixel square, usually uniformly distributed position. I didn't spell it very well. X, Y, and UV on the lens, and T in the shutter open interval, like we had last time. And what we want to do is add to the color this path trace, as I call it with an underbar here, of the lens position and this angle theta that depended on the lens position and the subpixel location. I guess I have too many. No, that's right, because that closes this parenthesis. Right? Last time I said, given the pixel position, you trace through the center of the lens, see where it hits a plane of focus, and then go from UV to that point, and that's your direction. Maybe you want to normalize it to make it a unit vector. And you just call this thing recursively doing the path tracing and returning a color, and that color is incrementing this color, and then you set the color buffer of ij equals the return at the color that you add up for all those samples divided by the number of samples. And that's the average color. That's your estimate of your integral. And so this gets you the direct illumination, because every time one of these rays hits a light source, you've actually added on the brightness of the light source. And it's also getting you the global illumination, because even if it doesn't hit a light source, it's going to get further light, further surfaces, and eventually one of them may be illuminated by a light source. So I think that's it for today. I'll talk about Russian roulette next time. So if you weren't doing this path tracing, you were just doing the color, then you just get the average color like we talked about last time.